Tom Coughlin, and I'm here with ICCE TV, and talking to Dr. Joseph Cavallaro, who is a professor of electronics and computer engineering at Rice University in Texas, Houston, Texas. And he just gave a keynote talk at the 2019 ICCE conference. And it was a very interesting talk, talking about developments of computer architectures, and also about development of MIMO and other communication techniques associated with the rollout of 5G and other advanced communications. Can you talk to us maybe first about some of the developments of computer architectures that are going to be, especially with changes in Moore's law scaling, they're going to be driving the next few generations of computer products?
Sure, exactly. Well, thanks again for inviting me to be here today and to give the keynote. I think one of the issues we're seeing is that as we're trying to go to higher and higher data rates in the communication systems, just a single core, single processor really can't cut it. And so we need to have some parallel hardware, parallel architectures to sort of integrate in and sort of help to do the processing. So there are a number of different approaches for this, and it kind of forms a heterogeneous system where you might still have a single core or multi-core processor as the controller, doing a lot of the finite state machine control, but then some accelerators that can handle some of the specialized functions. So let's say in communications, there's a lot of digital filtering, there's a lot of detection, a lot of decoding applications, which are very parallel. Essentially linear algebra type kernels. And so things like FPGAs to handle some of the more fixed function digital filters, and then GPUs, the graphics processing units, which then can handle some of the a little bit more irregular parallelism, I think become part of a very interesting system. And you see this especially in the emerging architectures for user equipment for cell phones between Samsung's Exynos and Apple's I series of processors, and also you see that in Qualcomm's Snapdragon processors, where there's multiple devices connected together inside one chip. But for base stations, it's a little bit different structure, because there are more discrete components combined and being able to support hundreds of users.
Mm-hmm. Do you think it's beyond just GPUs, isn't it? I mean, there's going to be a lot of different types of specialized processors.
Yeah, there will be. There will be. I think things that will be maybe more fixed function could eventually be hardened into ASICs.
Mm-hmm. Sure.
And especially, I think one of the challenges is the standards keep changing so quickly.
That's
so as the standards change, and it's not just 4G to 5G, but it's different flavors within those standards.
Well, right now, there isn't a fixed standard yet in 5G.
No, there isn't, but I mean, but
yeah.
different proposals, I guess
There's
I should say, right?
Right.
So Huawei wants this,
Right,
and
right.
Another Nokia wants that, and someone else wants something else. And so there's this whole, people are reluctant to freeze anything until the standards get set.
Right, right.
And then there's 6G is starting. There's
Yes,
some
I know.
folks in Finland that have a conference coming up I guess in February or March, about early 6G developments.
There's always new technologies for consumers.
Exactly.
And about the antenna technologies, so people are becoming familiar with MIMO and their network antennas, in type networks and things like that. But how is that going to differ from the neighborhood deployments that are expected for most of these 5G systems?
Well, there are a couple different directions based upon the carrier frequency. So in the so-called sub-6 gigahertz, which is kind of what we've dealt with mostly, nice propagation characteristics outdoor, nice characteristics indoor, you'll see arrays of antennas. I mean, already in Wi-Fi you see 4, maybe 8 antennas.
But it's a lot more, isn't it?
It'll be a lot more. It'll be in the hundreds. That's sort of the goal for the macro base stations to have hundreds of antennas. Now, when you're looking at millimeter wave, which is being used more for point-to-point communication, then they're in the 28 and 60 gigahertz range, and then there's a 78 or something also. Then those become much smaller antenna elements. So you can actually use them as more patch arrays. There have been some proposals, let's say, for high-definition video to distribute it within the house using millimeter wave technology.
Okay.
And also there's some proposals for fixed wireless.
That'd be a much higher frequency then.
Yeah, in the 28 or 60.
Right.
And actually there is, I think it's a 802.11x. There is one that actually has a combination of 2.45 and then I think 60. So you begin to see this kind of hybrid access points. But for fixed wireless, what essentially started out being WiMAX never really took off. People are starting to talk about having fixed wireless deployments, so that you might have a little antenna outside your house,
Right.
and that would be your, instead of a cable modem or fiber, you would have broadband via fixed wireless.
And that'd be sort of from the beamforming from the
Beamforming,
MIMO.
yeah, exactly. And since it's fixed, it's a little bit easier to then focus and also to be able to deal with channel variations. The mobility is always an issue with wireless systems, but if you're kind of static and not moving, then it's much easier to update the channel and not have to rely on the high data rate updates that happens if you're in a high-speed train, let's say.
And I noticed in one of your slides in your talk, you were showing the interrelationship, because these are not just passive radio devices. They're running on software.
Right.
There's actually a lot of computational computational activity going on.
Right.
So the computation and the communication are intimately connected. You
Yes.
were showing a chart as you had the number of antennas
Increasing.
per user increase, I think, wasn't it?
Yes.
Can you talk about that a little bit?
Sure. So with these massive MIMO technologies, to be able to get the beamforming, you'd have a larger number of antennas. So typically it's about a 4x kind of figure. So if you want to support maybe 16 users, they may need at least 64 antennas in that base station to be able to distinguish those users effectively. Otherwise, the beams are not narrow enough, they're too blurry, and you really don't get the benefits of the beamforming that we'd like to have.
You want to get the data rates you're after.
Yes, exactly. But that means also the A to Ds and the D to As are very high data rates, collecting lots and lots of data, which then puts other pressure on the rest of the system in terms of the buses to be able to handle 100 megabit per second data streams from, let's say, 100 antennas. It's a lot of processing. So there's a lot of concern also in the transmission side to be able to make sure that as we go from one high quality power amplifier to maybe 100 smaller, simpler, lower quality amplifiers. That was another topic of digital predistortion.
Yes,
You want to be able to
remember
clean
that.
up each of those small power amplifiers so they don't have interference among each other, reducing the signal quality.
Now, you were showing that as sort of a simple feedback, I think, mechanism for
Right.
doing that. That made me wonder, do you ever see that we might be actually using AI or, machine learning to understand changes in networks with continuous training to improve it even more?
Yeah, we actually did a study this summer where we took one of the older versions of these massive MIMO test beds and characterized each of the power amplifiers. The variations are not that great, but there's some temperature sensitivity
Oh, okay.
that comes into play. And also there's
Like at different times of day, too?
different times a day, and whether, how active, there's an issue with so-called peak to average power ratio. So if your signal is time varying and you tend to have a lot of ones in that signal, so to speak, then you kind of are sending out more energy than if you have a lot of zeros in that signal at a given
It's
point.
kind of an anti-compression approach.
Kind of.
Yeah.
But so we are really concerned about trying to handle this quality of the amplifiers.
Right,
It is a real concern for us.
So I think at the very beginning of your talk, say about every 10 years, we end up with a new change, a
Yeah.
major change in the network. So when do you predict, or what would be your best guess, and when we'll see 5G, in general usage, if not everywhere out in the boonies, but
Well, I think 5G is a bit of a blur
yeah,
because it sort of is,
whatever it is.
well, it's sort of a combination of a number of existing technology with a few new features. So I think you'll begin to see early deployments of 5G-like things in the next couple of years, but it'll probably take maybe another 3-4 years before you really could call it something that you would really consider.
Around 2023 or so.
Possibly,
Yeah,
possibly,
yeah.
something like that, where it'd be more widespread, Usually it's every 10 years for a new generation. I think 4G now is pretty well entrenched. What'll be interesting is if really 5G can meet the low latency goals that they're having, particularly for a lot of factory automation.
Right.
There's
Oh,
a
yeah.
lot of tight latency requirements.
A lot of
they're trying to-
IoT applications.
IoT
that kind of thing.
applications like
Yeah,
that.
Yeah.
So we'll see. There's a lot of software definition coming in, software-defined network,
Right,
software-defined
right.
radio. And that's to try to make it a little bit more future-proof, a little more upgradable. But anything that has software in it gives up a little bit of optimization.
Right.
So that's the other challenge.
Right.
But I'd say the next couple of years we'll begin to see some interesting stuff. And I think that the question then becomes the capital investment.
I was going to ask about that, yeah.
How much do operators want to invest.
Right.
I mean, these days, a lot of times
That's
they
a lot
don't-
of antennas. They're
a lot of
talking about.
antennas.
Yeah.
And you know, there are a lot of companies like Crown Castle that operate these antennas. And so will there be interest in actually upgrading? So I think it's still early in the sense of the research level for the massive MIMO. Still also early with the millimeter wave. And I think that's why I mentioned in the talk that National Science Foundation is sponsoring this Platforms for Advanced Wireless Research as a university industry and also kind of a government partnership
Right.
to be able to sort of sponsor and encourage people to try things out in a few places. So as I mentioned, there are 2 existing test beds. There's the one at Columbia, Rutgers, NYU. There's the one that Rice has with University of Utah. And there's actually requests for proposals out now, and they're evaluating probably 1 or 2 more platforms to be announced this coming spring or summer.
Okay.
So they're trying to kind of cover different topics
Right.
and trying to make so industry can try things out in an early phase and at scale, because that's one of the issues with a lot of these test beds. You want to do it at scale.
Right. Right.
If you don't have
Like
10
a city or something.
a city, or if you don't have lots and lots of users, you don't really get that feedback about what kind of interference you might have.
Yeah, exactly. Yeah, we'll especially do it in different kinds of, different areas of different,
Sure.
you know, climates and various
Definitely.
things as well. Yeah.
Definitely. I mean, Europe's doing something similar as well. They
You mentioned
have
Bristol, I think.
Yeah, Bristol.
Yeah.
And also Sweden, Lund.
That was the Linda's in Sweden.
Yeah,
Okay.
yeah.
Yeah.
Yeah.